This is Physics 2211, Lab 5, which is Choose Your Own Adventure, but I chose to do the falling slinky. Introduction. So the purpose of this lab was to model the movement of the bottom of the slinky as the slinky is released from the extended system. The fundamental physics principles discussed are Newton's second law, and gravitational force near Earth's surface. A brief preview of the results. So the computational model is a bit different from the experiment, as the experimental slinky falls faster than the model did. The system is the slinky. The surroundings are Earth, the hand that drops the slinky, and anything else that exerts a force on the slinky. The slinky is extended and being held up above the ground. Initial velocity is 0. The main physics ideas discussed in this are velocity and position updates, which both come from Newton's second law. So the velocity update is that the final velocity is equal to the initial velocity plus F net over m times delta t. And the position update is the final position is equal to the initial position plus the average velocity times delta t. And then the gravitational force is also another main physics idea, which says that the force of gravity is equal to the mass times the gravitational constant, which for Earth is negative 9.8 meters per second squared. And then I have some free body diagrams on the right. So before the top of the slinky reaches the bottom of the slinky, there is a tension force and the gravitational force acting on the slinky, which cancel each other out, so the bottom of the slinky doesn't move at all. And then after the top of the slinky reaches the bottom of the slinky, we only have the force of gravity acting on the bottom of the slinky, so it will fall to the ground. Here is my tracker video. As you can see, the bottom of the slinky stays stationary before the top of the slinky meets it. And then here's my code. For the mass of the slinky, I got it online. The position was from tracker and the velocity. And then the time and delta t were also from tracker. Line 43, g equals 9.8. And then j hat, which is just a direction vector for my update formulas. No, not my update formulas, my force formulas. And then lines 59 and 60 were calculating like that tension and gravity in the beginning. And then 65 and 67 are velocity and position updates. 84 starts a new calculation loop for when the slinky is falling to the ground and the bottom of the slinky isn't staying stationary anymore. So as you can see, it's only gravity acting. And then 94 and 96 are velocity and position updates. And yes, this is my entire model. Here is my code output and then the comparison graphs. As you can see, the red line, the experimental slinky, fell a lot faster than the model did. The experimental slinky has a more dramatic downward curve also, while the model gradually falls. The experimental slinky starts falling immediately when the top of the slinky reaches the bottom. So possible sources of error are discrepancies in placing the point mass in tracker, and then errors in the strategy of placing the mass. Also, there could be another force acting on the slinky that we were unaware about and therefore did not put into our model, which would have made the slinky fall a bit faster. Or also the mass that I got online for the slinky could have been inaccurate for the slinky that was used in the YouTube video that I took the tracker data from. Okay, so the experimental slinky might fall faster because when the two ends of the slinky come together, the top of the slinky might exert a force on the bottom of the slinky, giving it a little push, and therefore that would make it fall a bit faster as it would have more momentum. And then we might be able to model this force using Hooke's law, which is the spring force equals negative kx. And then we would need the spring constant of the slinky to do that. And then overall, our model is accurate if gravity is the only force acting on the slinky. So there must be another force that was unforeseen and unaccounted for, which would have caused the slinky to fall faster like we saw that it did in our experimental model. So overall, my hypothesis is that the top of the slinky gave the bottom of the slinky a push, and also the slinky didn't fall uniformly. It kind of turned after the top met the bottom, so that might have also caused some error in our experimental versus computational data. Okay, so thank you so much for watching. Bye!